Let's start.
Okay, today we will discuss presentations, embeddings, and automorphisms of homogeneous spaces for SL2. This talk is based on the work by Freudenberg with the same name. And first of all, let's fix some ground field. As usual, I will denote it by K, and I require it to be algebraically closed and of characteristic 0. So in the situation where some linear algebraic group acts on some irreducible affine variety, we provide some definitions. So by presentation, we mean the following thing. Presentation of the pair G and X is just G-equivariant closed embedding of X to some affine space AN. This is closed embedding, and we see we have some J action on X, and here we require J action on AN2, and it should be linear. So actually here our variety is embedded in some finitely dimensional J model. And from classic theory, of course, we know that we always can embed X somehow with different maybe dimensions of affine space. And if this dimension is minimal, we call the presentation minimal. So let's fix it. Presentation is minimal if such n is minimal.
So there may be several minimal presentations.
Yes, and we will consider one example where it happens. The dimension of AN will be the same, but the actions of J on X will be different. So we will discuss it. And here I need some notation. Let's fix minimal presentation dimension of the pair X and J. J here is necessary too, of course. And this will be minimum of such natural M that there exists closed embedding of X in n-dimensional J model. Okay, and let's fix another thing, another number. By embedding dimension of X, we mean minimal such M that there exists some embedding of X in AN as closed subset. Of course, this definition depends only on X. And okay, if we have some algebraic action of J on X, let's give the following definition. We say that action of J on X is absolutely unextendable if J equivariant link X to AN and N is this action to be linear. It is just algebraic action. It is not necessary linear.
No, something strange.
We fix n is a dimension. So is false. Action is absolutely not extendable if we cannot embed x in such minimum affine space in such sense. We cannot extend our action.
Right on, this is equivalent. The infinite dimension is slightly bigger than
Here it is linear action. Maybe it happens that, for example, in dimension 5 there is linear action, but in dimension 4 it extends to algebraic.
Just embedding dimension is equivalent embedding and linear equivalent embedding. Of course, each of them is not less than the previous, but maybe sometimes they are equal.
Yes, I think it's true. So during the last talk we discussed two homogeneous spaces for SL2. Let me remind them. So X is a homogeneous space of SL2 by N, where N is a normalizer of maximal torus in SL2. Y is homogeneous space SL2 by torus. And here is plan of my talk. First of all, let me give two examples, two surfaces with absolutely non-extendable actions. Then we provide minimal presentations of affine SL2 homogeneous spaces. In this point I will give some sketch of a proof, since there are a lot of technical details. And the third one, we will discuss some inequivalent embeddings of y to A3, of course as a closed subvariety. Okay, let's move to the first part.
Inequivalent in which sense?
Equivalent in such a sense that y is isomorphic to the set of zeros of f, isomorphic to the set of zeros of J, but there is no automorphism of A3 which moves one to another.
So without any action, just as a variety.
Yes, here we prove that there is no such automorphism, and we do not require it to be G-equivariant or something else.
There is no action of G in this case, right?
In this case, yes, we do not consider it.
If you remember, we already discussed some paper by Coleman. This is called extension of automorphism. Say you have some space, you have two subvarieties, they are isomorphic. Can this isomorphic be extended to automorphism of an ambient affine space? And it was known also that this is not always the case. And this is one more manifestation, this is not always the case.
Actually, if I'm not mistaken, for y, we can extend each automorphism.
You have two realizations of your y.
Yes.
So you have these two subvarieties.
Yes.
You have an isomorphism of this copy of y with this copy of y. And
Yes,
the
I
question
have.
is, can this isomorphism be extended to automorphism of the ambient affine series space?
Okay.
And you say that there is no such phi.
Yes. Okay, so the first part, two surfaces with absolutely non-extendable actions. Значит, first part consider that of course we can write it in a three-dimensional fine space. It is isomorphic to the set of zeros of x, y, z minus 1 here. So it is of course closed. And here we see that the dimension of x is 3. Surely we cannot write it in two-dimensional space. So then consider some group J. We define it as following. So it will be a direct product of automorphism group of one-dimensional torus with itself. And this group acts on X just component-wise, right? So first of all, I claim that minimal presentation it is linear algebraic since this is isomorphic to torus and to semi-direct product of torus and of course, since yes, so it is algebraic, it is okay. I claim that minimal presentation dimension of the pair x and j is greater or equal than, and why is it true? Otherwise, if we assume that this action extends to action of three-dimensional fine space, then and to some linear action, we have map from J to J3 over C. And I claim that since action of J on X is effective, this action is effective too. So this is actually inclusion, contradiction.
There is no three-dimensional representation of this semi-direct.
He says so.
I think that we have this, then G contains two-dimensional torus. In G3, this should be the maximum torus, and all G should be normalizer of this torus, and we know the normalizer.
So GL3 has a three-dimensional torus.
Oh, it's a
serious problem.
Okay. Okay, he claims there is no faithful representation of J on C3, and that's all. Okay, let's move further. And
so this is an exercise for us, because at the moment this is not clear why we don't have faithful.
Actually, yes. If we cannot use centers, then it is not clear for me now too. So let's move further. When we prove that minimal presentation dimension of X and J actually equals to 4, and here we construct an action of J on the four-dimensional space, which is linear, and it restricts to such action on X that we want. So, okay, let's construct such action first of one copy of automorphism group of torus. So, of course, it is semi-direct product as it was discussed. And consider such action on A2. Here we have element T, and here we have element tau, which is not neutral. And element T acts on the pair xy, and we got tau Tx inverse to Ty, and tau acts just like permutation of them. So, okay, Now, consider two such copies. Which is G, and it will act on a form component-wise. Okay, then note that the idea generated by xy minus 1 and w minus 1, here we have coordinates xy, z, w. Note that this idea is G-invariant in polynomials of x, y, z, w. Since this idea is G-invariant, can consider, of course, we always can consider homomorphism of factorization by this idea. So this homomorphism will be G-equivariant. And of course, it is clear that this algebra is isomorphic to a coordinate link of our X, which is two-dimensional torus. And maybe we need to check that. This is now the equivalent surjection and surjection, and we can consider dual map. So from the X to four-dimensional affine space, since it is surjection, this is inclusion, it is embedding, and let's show that yes, it is of course closed embedding. And this is G-equivariant. And you can see that if this algebra has generators, maybe not X, it has generators, okay, X, X minus 1, Z, Z minus 1, and X, Y, Z, W map to these generators under this factorization. So you see that on these elements are acted by permutation, and here tau acts by permutation too, and element of torus acts with weights here like 1 minus 1. And this is just what we wanted for our two-dimensional torus. Okay?
This is absolutely clear. So
this is absolutely clear.
In two-dimensional space. And product of two components is embedded diagonally, not diagonally, but component-wise is in the A2 by
yes, it is true. And here let's show that an action of the action of J on X is absolutely non-extendable. Absolutely non-extendable. And here we use the following theorem. I'll give a number since I want to refer to it later. It was proved in a work by Kraft and Russell. It's 14th year. And it claims the following. If J is some non-finite reductive algebraic group over the field of complex numbers, and it algebraically acts on A3, then this action is linearizable. And to prove that the action is absolutely non-extendable, okay, we suppose it is extendable. So we suppose that we have some embedding of x in A3, we said that embedding dimension is 3. So x is isomorphic to some s in A3. This is, of course, some closed subset, and we suppose that action of j here extends to action of j here. Then we use theorem 1,4.
We have then again inclusion into GL3.
Yes. We see that this action is linearizable.
By 3.
N is 3, right? It is linearizable, and again we have inclusion from G to GL3. It is contradiction. So let's give here some conclusion for such x and for such j and for such action on x. We have that minimal presentation dimension is 4. By the way, embedding dimension of x is 3, and this action is absolutely non-extendable. And the second example of this with non-extendable action is the following. Now consider direct product of one-dimensional torus and the finite line, right? And of course, it is embedded in three-dimensional space as the set of zeros of xy minus 1. So it is closed here. So yes, embedding dimension is 3. Then consider the following group. It is again built from automorphisms of torus. Now it is just automorphisms of one-dimensional torus. It is semi-direct product of torus and Z2. And here, firstly, I would like not to fix the action of j on x. Maybe I will consider some action of j on A4 such that it is restricted to x, and then we will consider this action. So fix some natural number n, and we require it to be odd. Yes, so it's not divisible by 2, and here we have the following action of j on A4. Recall that we can consider here element t and here element tau, and t acts on coordinates a, b, x, y with the following weights. So here t minus 2a, t to b, t minus nx, and t ny. And tau acts by permutations. By permutations. B, A, Y, X. And note that since X is odd, this section is effective, right? And then again given, we consider some G-invariant ideal. It is generated by AB minus 1 and x plus a and y. It is isomorphic to x, of course. This is just coordinate. And AB map to coordinate function on one-dimensional person inverse P. So this is isomorphic to x, and we have embedding of x in A4, and it is J. It is closed, of course, and x is G-invariant, so this embedding is G-equivariant, and now we need to understand how G acts on x. Let us consider again the homomorphism of factorization from coordinate ring of A4, so AB xy, surjection to coordinate ring of x. So this is such factor algebra. And yes, again, this is G-equivariant. And then it corresponds to the embedding of x to A4. Here, let me choose generators. This is R minus inverse to R, and S. And we see that here A maps to R, B maps to R, to inverse to R, and to S it is mapped Y. Okay.
It's not clear why coordinate invariant with respect to tau.
Can you repeat, please?
So you mentioned this coordinate x plus a to the power n y, right?
I don't get that actually.
This ideal is invariant with respect to the whole group.
It is J. Yes, I claim that this invariant, this ideal is J invariant. Since when we multiply these two elements, we got AB again, and here A and Y. Where is it? Here I need to check it. And Y is
So maybe it can be expressed as a polynomial of these two initial polynomials.
No, it's okay. This is multiplied by t power minus n.
And x is also.
And x is also multiplied by t power minus n.
That's okay.
That's okay.
Oh, so it's
okay, yes, this is t minus n ay, and x is
A power n y.
a power n y, right.
But what
Yes, and x is multiplied by minus n by t to the power minus n2. So
And now let us look to permutations.
The
Let
question
us
was
look-
about tau.
question was about tau. Okay, let's see. This is clear. We switched with P, and this is maps to this. And the question is, why is it in our ideal?
But b is a minus 1, power minus 1.
Ah, yes.
And you can multiply it by invertible element and obtain it.
Mm-hmm.
If you multiply by a to the power n, yes.
If you multiply this thing to a power n, then everything can
If you multiply this thing with e to the power n,
due to first relation. AB minus 1.
Yes, it is in I. It's true.
So we can multiply.
By inverse to yes. So here we go by this. Okay. Okay. So now we need to understand how J acts on X. How is it restricted to X? Look at the following action. On the element here. When we apply t to R and S, actually write it, R is multiplied by t minus 2, and S is multiplied by t to the power of n. It is evident from these maps, actually. We know how t acts on A, B, and Y. And under the action of tau, this pair maps to R to the power, inverse to R, and R and S. And, okay. So, here we see we have some action of J on X, which is which extends to linear action of J on A4. Here we see that embedding, not embedding, I'm sorry. Here we see that minimum representation dimension of X and J is not greater than 4. Okay, then let's show that actually it is 4. By the same arguments as in the first example. So I claim that minimum representation dimension of X and J is equal to 4. Since before, suppose that X is as X it is hypersurface in 3-dimensional space. We take 3 since 11 dimensions it's hypersurface. And suppose that this action extends from S to C3. Okay, by theorem 1.4, this action is linearizable. So, actually, the action, so this is a linear action, it is presentation of G, and it is given by the images of elements T and tau. So it is given by rho tau, rho T. Can be shown that it has the following form with some choice of basis. The first vector multiplies by t to the power of m, the second t minus m, and the third is invariant. And is given by rho tau, for which we have two cases. So it is alpha or beta, where alpha is the following matrix. We switch to basis vectors, and preserve the third one. Or we can switch vectors, and the third one is eigenvector with eigenvalue -1. Okay, so now first we want to come to some contradiction. For this we consider fixed points of alpha, beta, and tau on x. So let's do this.
Do we can prove that embedding?
Yes, sure. It is example of non-extendable action of the surface, and yes, but it is a bit more interesting since we consider, first of all, we consider tau fixed points on V. So we understand how tau acts, see that R equals to its inverse, this equals to S, and we have the following. Either I equals to 1, either it equals to -1, but in this case S equals to 0, right? So here we have 1 plus some related point. And then consider, first of all, beta fixed points. Beta acts around C3, so on C3. I think it's obvious. First two coordinates are equal, and the third is any. And here we have line. Third coordinate is 0, of course. This line x 0, x in C. Okay, we see that it is not our case, since we have some hypersurface. Here we have fixed points, line and 1 point, and in whole space there are less fixed points than in X. So it is not our case. So rho tau is not beta. Consider alpha fixed points.
This line does not lie on V, right?
This line does not lie on V.
Yeah,
We don't know. We consider any embedding, right? It can lie on S, but what should we do with this isolated point?
the isolated point can be anywhere, not necessarily in.
But when we embed X as S, this point is fixed by tau in S, so it is fixed by beta in C3, right? So it is not a case. It is too many points. Maybe I will save this. So, of course, for alpha, we see that fixed points form a plane. The two first coordinates are equal, and the third is any. Anyway, here we get contradiction 2. We understand that here we take alpha fixed points, they form a plane, and we intersect it with hypersurface, and it cannot be so that some irreducible component of our intersection is 1 point, right? So I claim that the dimension of any irreducible component of hypersurface and two-dimensional plane is, of course, 1. So it is 2 minus 1, it is 1, but we cannot have point. And it is...
The first row V is S or tower fixed?
Is first row...
First row?
First line.
First line. V is S
6
or V
points
is
on V, what is V?
So yes, it is our variety X, so yes, or S, if you consider it embedded. Okay, here, contradiction. So we see that we have just two cases where row tau is alpha or beta, and we have contradiction in each of these cases. So, okay, I think we can give some conclusion. If we take such variety, direct product of dimensional torus and define one, and we consider it with the action of J, which is automorphism group of one-dimensional torus, with such action, then the presentation dimension is 4, and action on X is absolutely non-extendable on C3. We take C3 since embedding dimension is 3. Okay, so it was the first part of my talk.
Okay, but in fact these two examples are more or less similar. So let us go fast.
Okay. So So the second part of my talk is the minimal presentations of L2 homogeneous spaces. It was mentioned last time, but we constantly. So homogeneous space. Of course, it is true not only for S32, but I consider S32 homogeneous spaces. Then that it is affine if and only if H is reductive, and it happens exactly in the following cases. Either H is maximal torus in SL2, either H is its normalizer, so of course it contains torus, and it contains such, I think, and it's all with surfaces, but actually there are cases where H is finite. And here exists some classification, and I will discuss it a bit later. First of all, let's deal with torus. So SL2 by torus is a variety which we denote by Y. And the standard embedding is the following. It is the set of zeros of xy minus z squared minus 1 in C3. And we can find such result in work by... Okay, I'll give two references. First is Danilov and Gizatudin from 77th year. And the same thing we can find in work by Makardamanov from 90s.
There are two authors, not just one?
Makardamanov is
Okay.
the unique author, if I'm not mistaken. think we checked. Okay, the theorem claims that each automorphism of Y actually can be extended to automorphism of C3. So these are exactly such automorphisms of C3 that preserve Y. In the work by Makardomanov, actually it is there is some list, and he proves what automorphisms are here. And there are some families, and each of them actually extends to C3. So, okay, we see that there is actually no non-extendable actions on Y. It is corollary from this theorem. There exists no non-extendable J actions on Y. Since if it exists, each automorphism we can extend, and we have.
So in this case, G is
absolutely non-extendable. What?
G is SL2.
Of course, yes. Acting group from now is SL2.
That's true for any group.
Is it
Any factor on Y?
Yes, it is true. There is no non-extendable algebraic action of any algebraic group on Y. Yes, since if it is, then we can extend it, and we extend it. Okay. And case where H equals to normalizer of torus, it was discussed last time. Here we denote by X the homogeneous spaces SL2 by N. And let me just formulate some theorem which Polina proved last time. And I formulate it in such a way. Minimal presentation dimension of this pair, X and SL2, is 5. And embedding dimension of X is 4. And action of SL2 on X is non-extendable. Absolutely non-extendable. So we can embed X in 5-dimensional space such that action of SL2 extends to linear action. We cannot embed X in 4-dimensional space such that it extends to any algebraic action, right? And to 4-dimensional we cannot, since it is non-extendable. When we say about extendable or not, we require here embedding to space of dimension of embedded dimension of X, right? So
the intermediate number is also 5.
What does it mean?
There were 3 numbers, right? So 3 dimensions.
Equivalent.
Okay, here we mean to A4, of course. Okay. And finally, the third case is the third case of reductive subgroups in SL2 is finite subgroups. So finite subgroups in SL2. Here, the author gives just a list. I'll do the same. It is according to work by Felix Klein, 1884, and the list is the following. First, there is a cyclic group. Okay, there is cyclic group. There is binary dihedral group. Here we require n to be greater or equal than 2. So it is binary dihedral group. Have B to 24. it is binary tetrahedral group. We have BO 48 binary octahedral group, and this one, it is binary icosahedral group. Icosahedral group. Okay, then the author constructs minimal presentations for these homogeneous spaces. No, for homogeneous spaces of these subgroups. Maybe I will give minimal presentation dimension for them right now. Here we have the following cases. If it is Zn, then if n is 2 or 4 divides n, then it is n plus 4. Otherwise, it is n plus 1. So it is here. And in other cases, we have 2n plus 1. We have 7, 9, and 13. And now I would like to give some sketch of proof. Okay. So,
what about embedding dimensions? Or you discuss it later?
Embedding dimensions. I don't plan to discuss embedding dimensions.
Okay.
In the paper, there is just okay, I will say it now. He constructs presentations, and then he proves that they are minimal. But he says nothing about extendable or not these actions. So recall some information about fundamental pairs. Of course, it was last week, but I decided to change all notations, so I need to fix them. Let me be affine K-domain, and let f and e be some locally important derivations on B. Definition. We say that pair f and e is fundamental if, let me fix, for h equals to the commutator of e and f, we have the following. H and f, commutator of h and f is minus 2f, the commutator of h and e is 2e, right? So, of course, it is these are relations that give standard SL2 triple. And recall that if you have the, if you take SL2 action, okay, I claim that there is a bijection between the set of SL2 actions on B and the set of fundamental pairs for B. And the idea is the following. Of course, if you have a SL2 action, you have an action of one-dimensional unipotent subgroup here. It is isomorphic to GA, and it acts on B. So you have LND, and it is, if I'm not mistaken, E. You have some LND E. You take a lower triangular matrices. And in the same way, you have another LND. And maximal torus of SL2 corresponds to some derivation, but not necessarily locally nilpotent. Actually, it is not locally nilpotent. This is multiplicative, it is isomorphic to GM, to multiplicative group of our field, it acts on B, and it gives rise to, denoted by H, it is derivation. And it can be shown that, of course, since this derivation corresponds to the action of one-dimensional torus, it is semi-simple. So H is semi-simple, which means that it has basis of eigenvectors, and it gives us the grading on B. This is the grading. And of course, in component D, we take the following elements, such that when we act by H, we take dB, we have dB, right? So denote kernel of F by A. A has the grading too. Actually, there are no negative components. So here B is natural number, maybe 0, of course. And for each homogeneous element from the kernel of degree n, we consider F hat, which is the following space. We take all images of degrees of E. We take vector space with basis F, EF, E squared F, etc., E, D, F. It's obvious that E acts in this direction, and if we apply F, it will act in the opposite direction, but with some coefficient. So here we have E, D minus I plus 1, E, I minus 1, F. And of course, H resolves components, it multiplies it by some scalar 2, something like 2I minus D. Yes. Okay. So if we take algebra generated by these elements from this space, we actually have the smallest F and E invariant subalgebra of B such that it contains F.
What you are proving now?
I give some construction.
For what?
For constructing many dimensional presentations of these homogeneous spaces, with such group, for finite groups.
Why do you need elements for finite groups?
The point is following. Maybe some idea here. Last time we discussed that if kernel of F is generated by some elements F1, etc., we can like integrate it. We can construct this f hats. And these elements generate OB, right? There was lemma, I will recall it. And what do we need? The idea is following. Can consider the standard SL2 triple. So, okay, there will be some psi and epsilon to be a fundamental pair for SL2. Then A will be the kernel of psi, and we consider H invariance. Here H is subgroup in SL2. And we will show this, it is actually evident, that that is two-dimensional algebra and its invariance, and generating elements for these invariant rings are given. There is some list. The author does not prove it. But there will be some lemma which claims that BH, which is of course coordinate link of SL2 by H, then it is can be obtained in such a way, right? Take hats on our Fs and generate algebra. Okay. So here we can construct irreducible modulus of SL2 of Vn is n plus 1 dimensional module here. And this will be surjection, and this will be SL2 invariant surjection. So again, it will correspond to the embedding of spectrum of such algebra into A in big dimension R plus the sum of D. And then he shows that this is minimal presentation. So this is why we need fundamental pairs.
So, since H is a subgroup, for example, of finite subgroup,
H is
finite subgroup.
finite, right?
Since it is contained in SL2, it acts on two-dimensional vector space. So we may consider algebra of invariance of this H on the polynomial in two variables.
Yes.
Okay. So certainly the generators of this algebra of invariance is classically known.
Yes.
The hydral group for icosahedral group and so on. The claim is that looking at this, you can describe the algebra of H invariant on SL2 itself.
Yes.
This construction of passing from F1 to F1 hat.
Yes. It wasn't mentioned, of course, B is coordinate link of SL2. Yes.
And the claim is that it gives you the minimal equivalent embedding of the corresponding three-dimensional homogeneous space.
Yes, but it is not a claim, but he proves it in each case for each finite group.
This is a claim, and he proves this claim in each concrete case.
Yes, yes, okay, yes. So this is plan. Okay.
And what about SL2 over n? This was done previous time, right? Is that
SL2 modulo n, it is, we discussed it last week. It was on Polina's talk, yes. Okay. Maybe we can okay, so this is plan. And
Understand this problem. Can you please? This is plan forward.
this is a plan for constructing minimal presentations of homogeneous spaces of SL2 by H.
But not for proving this minimal.
Not for proving it is minimal, yes. And
Is it true that the polynomials f1 and so on fr are homogeneous and d1 and so on they decrease?
yes, it is true. They are homogeneous and they are in kernel of psi. So here, maybe I'll give it step by step. Now,
And this will be the end.
I wanted to discuss not equivalent embedding of y.
Maybe this is more interesting.
This is more interesting. Okay.
So what will be the conclusion of this part? For each finite group, you say that the, how you call it, a minimal embedding dimension is known after Klein, because this is precisely the number.
Right. No.
So what is the aim of this part? To show that minimal presentation dimension is not the same as minimal embedding.
No. The aim of this part is to construct minimal presentation.
Okay, but is it? But do you know what did you mention about Klein? What was the result of Klein? Only finite subgroups
Not only,
numbers,
but these lists for invariants of finite subgroups on our plane.
So for any finite subgroup H, you have number R. This R is a minimal embedding dimension for the algebra of invariants. But this is not connected with the homogeneous spaces of SL2.
You claim that R is not.
There was a statement, but it is now erased, about 7, 9, and 13. As it's there,
This
these
is
are
the minimal
dimensions.
presentation of dimensions
Of what?
of this list.
But what do you mean by list? With any H, you may connect the algebra of invariants and its spectrum.
There was no statement about this.
And
There
was a
was-
statement about SL2 over H?
It was a statement about minimal presentation dimensions for each finite group, for each homogeneous space, for each finite group. Right? The n, bd for n, bd 24, b like this. And here we gave some table, minimal dimension, minimal presentation dimension. And yes, it is something like 13, 9, 7, 2n plus 1. And here there are two cases, n plus 1 or n plus 4.
Okay, so this is a result of Freudenberg.
This is result of Freudenberg, yes.
And what is the minimal embedding dimension? This is not known.
I need to think about it, search for it. Is it equal to R or not?
R is a minimal embedding. Can you write down some
Yes.
new variety, Z, which is C2, quotient by this finite group H. This is also some surface, right?
Yes.
And this is this F1, Fr. These are generators of the algebra of homogeneous of regular functions on this surface, right?
This one, this, yes, it is true.
So it can be extended from Klein results that this R is an embedding dimension of this variety Z, but not of the
Yes.
homogeneous space.
I understand. Okay. You claim R is embedding dimension of Z, and you don't know how it.
Because this algebra is graded, and these are minimal homogeneous generators.
It seems that it's have a non-regular point and maybe a tangent space, and this non-regular point is this dimension. But there is no connection.
Hillenburg computed minimal representation and minimal dimensions of these homogeneous spaces are not discussed, right?
It is not discussed in this article, right?
Okay, I propose to skip the proof, and we still have some time to discuss non-equivalent realizations.
Okay. So first, I will. Yes, it is the third part. Inequivalent embeddings y to A3 as, of course, closed subset. So theorem claims the following. We consider the following polynomials in three variables. P is xz minus y squared, f is xz minus y cubed, okay. R is yf minus x, and j is x inversed f fourth plus r cubed. These are elements of just C of our, these are polynomials. X, y, z are independent. And he proves, he discusses the following. First of all, for any xi, which is non-zero element of non-zero complex number, can consider fiber of xi of pi and of j, and it will be isomorphic to y. Maybe I need to recall that because y is homogeneous space L2 modulo T, it is isomorphic to set of zeros xy minus z squared minus 1 in A3, right? So this is our standard embedding. He proves that for such polynomials, each fiber, each non-zero fiber of P and J is isomorphic to Y. Then he shows that, actually he says that it is well known, but for any xi from C, the fiber of xi is normal. So each fiber of P is normal, but the fiber of zero of polynomial J is not normal. Maybe I'd like to give some corollary right now. So I claim that there is no such automorphism of C3 that maps the fiber of J, the fiber of unity of J, to the fiber of unity of P. And each of them is isomorphic to Y. And because if such phi exists, there would exist such phi star that takes P and maps it to J. And it is not our case, since, for example, the zero fiber of P is normal, but zero fiber of J is not normal. So there is no such phi star, and we can conclude that there is no such phi too. And here we have two embedding of I. All this situation, of course, in C3, right? We have two embedding of Y in one space, and they are not equivalent. So one is not mapped to other by automorphism. Okay?
Can you just again explain what is idea?
What is who?
This is corollary.
Corollary. I claim that there is no such automorphism that maps G fiber of unity to G fiber or to P fiber of unity, right? It is true since their fiber are really different here. And the point A tells us that each of these fibers is isomorphic to Y. Yes? So there is no such automorphism.
So we can just look at these polynomials and we'll see that.
Yes, we can look at these polynomials and conclude that if there is such phi, then there is such phi star that maps P to J. Then there is such automorphism that takes J minus 1 of 0 to 0 fiber of J to P fiber of 0, but like automorphism. But it is not true since one is normal, one is not normal.
Okay, so idea is very clear. You take two polynomials and you put one polynomial equal 1, another polynomial equal 1. You obtain smooth surfaces, and it turns out that these smooth surfaces are smooth quadrics. Okay? But when you consider cone version of this hypersurfaces, when you put these polynomials equal to 0, you obtain two different cone. One is normal and one is not. So they cannot, we cannot send one polynomial to another by automorphism. But how to prove that 0 set of G is a smooth quadric?
How to prove that? He uses local slice construction and Dayevsky surfaces. Maybe I can give sketch of a proof.
Can you write down what is G? Because G is given not explicitly. Can you write down G as a
I think no, there are some calculations. He doesn't do it either.
Okay, so if it is a difficult polynomial, how can we prove that it defines smooth quadric?
He takes such so let B be coordinate ring polynomial ring XYZ as before. He considers three locally important derivations. They are given by in the form of Jacobian derivations. Like delta 1 is Jacobian derivation of x and f. Delta 2 Jacobian for f and h and j. Delta 3 is delta j h. Of course, this notation means the following. It is a determinant of matrix here. So he considers these locally important derivations. By local slice constructions, what is h? Yes, h is...
Ananya is active when we speak about many locally important derivations.
H is the following polynomial, and from local slice construction we have the following claims. All of them are LEDs. Then we can give explicit generators for the kernels. Here kernel delta 1, of course it contains x and f, but nothing more. And when we apply it to R, what is R? R is this polynomial. We have xf. So R is local slice for D1. And the same things are happening here. Kernel of D2 is algebra generated by f and j. Kernel of D3 is algebra generated by j and h, and it acts on R and maps it to j h. Then he considers For each non-zero element of field, he considers B bar, which is factor algebra of B by polynomial G minus A. So it is just coordinate ring of our A fiber of J, okay? And we will denote in such a way this mapping. We will draw bar here. So first of all, claims that spectrum of B bar is smooth. I think it can be checked explicitly, but he does not do it.
You can write down the polynomial, take all the partial derivatives and...
Yes. But I think it is really many calculations. So since it is smooth, it is of course normal. And then we see that J is in kernel of the delta 2 and delta 3. So delta 2 and delta 3 are restricted to our factor algebra. And we have delta 2 and delta 3. We build delta 2 and delta 3 in. They are locally important on B bar. Then
this is how you construct essay to action this way.
Actually, this is how we prove that Makar-Romanov is trivial. So the kernels, I write it right now. So our aim is to prove that Makar-Romanov of B is just constants.
Okay, if we will prove this, what it is?
Then we use the theorem of Daigle, and it says that if we have two non-equivalent locally important derivations and some okay, I will just prove it, not prove, formulate it here. So it is Daigle. So B is K-domain, Y is some element of B, and D1, D2 is some element of some pairs of LNDs here. So let the following condition hold. Kernel of D1 is not equal to kernel of D2. It is proved in this step, actually. It is easy. And kernel of Di is polynomials, and I is local slice. So Di maps Y to kernel, but not to a zero element. In our situation, if I'm not mistaken, it is R. So we can compute that when we apply delta 2 to R, R is image of R bar is image of R. We got AF, delta 3 of R is AH, and by the way, we see that since HF equals to G plus R squared, have that product of the images is A plus R squared, since it's so obvious, J maps to A. So here we have some relation, and we prove that nothing more here. So then he shows that I'm sorry. So the claim is the following: if we have these two conditions, then B is the Milevsky surface. does it mean? It means that it is isomorphic to the set of zeros of xy minus p t. Oh, is it? And this polynomial has simple roots.
Okay, assume that we have this theorem, and why is it correct?
Then B bar is generated actually by elements F bar, H bar, and R bar. And he says that since this is just
From this, it's obvious that this is smooth. But you, of course, said that this is smooth, so it's not interesting.
yes, but we already have a relation in our B bar. Yes, and he says that it is a prime relation, so actually
This is a quadratic relation.
it is isomorphic to, like they are independent. It is xz minus y squared minus a, right? And that's all. So we started from, actually B bar is coordinate ring, let me write it. It is coordinate ring on our G fiber of A, right? And he proves that it is isomorphic to this. So, okay, now we see that each non-zero fiber of J is actually isomorphic to our variety.
I cannot see the relation of the claim that this is the Danielewski surface with the claim that this is generated by H bar, F bar, and R bar with these relations.
Yes, actually this is a problem.
Isn't it fall from multiplied theorem that multiplied
I look at theorem about local slice, and I have something about the kernel of derivation. It does not claim anything about your domain.
Okay, time is over. So the technique is clear. My naive suggestion will be you have these two LNDs, right? They are given explicitly by formulas. You may compute their commutator. And hopefully it will appear that this is a SL2 triple. So you have a SL2 action on this surface, right?
I'm sorry, is it evident?
Small delta 2 and small delta 3.
Yes, we have.
These are concrete LNDs. They are given by this formula upstairs, right?
Yes.
You can take these derivations and compute their commutator.
Yes.
And it will be some semi-simple derivation.
It will be simple
And
derivation.
then you can compute the semi-simple derivation commutator with them. And hopefully you will obtain SL2 triple. So they will commute like a 3 basic vector in SL2.
But why we get SL2 triple here?
I hope.
Is it okay?
And
I'm not sure if it is true.
what is the conclusion?
It will imply that the group SL2 acts on your surface.
Okay.
Yes.
This is a smooth surface with a non-trivial SL2 action. So in this case, this is either SL2 over T or SL2 over N. But SL2 over N, as we know, is not a surface in three-dimensional space. So this can be only SL2 over T.
Yes, but I think it's a little bit longer than our life to compute this commutator.
No. Experienced researcher take two hands and compute any commutator. So
Sorry, so in particular we defined logic in A3 by an equation of degrees, 11?
Well, the trick in 3,
It's wrong.
it's, yes, 11. It is isomorphic.
It's the same A3.
yes, wait, simplest.
I don't know, it just sounds impossible. Just looks silly.
It's a very bad
Very bad what?
embedding.
So what's the problem? The problem is that our embedding looks sillier.
Impossible. So the result is good because it looks impossible.
But it is proved. So let's have. Okay, maybe that's all.
I actually don't understand the general idea. So we wanted to construct an equivalent embedding of y to A3, yes?
Yes.
And why we constructed it by this theorem?
Why what? We can, sorry, can you repeat please?
We have this theorem. Why this theorem implies that we have this equivalent embedding?
Doesn't.
No, it is not about equivalent embedding. Here we do not equivalent. Why is it? We call embeddings
which cannot be sent to each other by automorphism of ambience.
So actually, this is definition of inequivalent embeddings, and by definition, they are so.
G is
such.
G is a polynomial here. This is very to denote.
Yes, it is problem.
The second row in this diagonal theorem, which said that this I is a local slice for such a derivation, and our H and F are somehow local slice due to these derivations, and maybe this explains that xy is this H and F, but I'm not sure about this.
Okay, any more questions? Then I have a question for our audience. So if you understood what happened today, we discussed that we can consider just embedding of Veronika, yes, without any group action. Then we can consider equivariant embedding with respect to some action on the ambient affine space. And then we can consider minimal embedding with respect to equivariant closed embedding, minimal dimension with respect to equivariant closed embedding into G model with a linear action. What Veronika today explained us is a Freudenbuch's example that minimal embedding can be different from minimal equivariant embedding with respect to G model. And can you give an example when minimal embedding in G model and minimal embedding in a affine space with some, not necessarily linear action, is different? Right?
Minimal embedding in G model and in affine space are different.
I think this will be very difficult to construct such examples for reductive group, because for reductive group we either have a theorem that any action is linearizable, or there are counterexamples to linearization problems, so there are some examples of non-linearizable action. But they are very difficult and they are very similar to action on G models. They are constructed as total spaces of some vector bundles or some G models, and in this way it's no chance to construct such counterexamples. But let us take non-reductive group. For non-reductive group, can you construct GA? Okay, give us concrete examples. 2 minutes. Okay. No example. Which one?
GA.
Assumed for GA.
What is a variety and what is a group and what is a?
GA acts on GA.
Yeah.
By translation.
Right. So a non-equivariant but non-linear embedding is 1, and equivalent linear embedding, dimension of equivalent embedding into linear is 2. Okay, so I propose all people here to think about it. Okay, thank you very much.